Hi everyone, this is a lesson on implicit differentiation. So explicit functions and implicit functions, that's the first thing we need to understand. X squared plus y squared equals 25, right? That's the equation of a circle, radius 5. And this is called an implicit equation because y is not all by itself. Y and x are sort of jumbled up together, right? This is an implicit equation. If you have the same equation where you put y alone on the left side, if you did on the left side, by just subtracting x squared and taking the square root, you'd get an equation that looks like this. This one is called an explicit equation because y is alone on the left side, y alone on left side, right? So this is explicit right here in red, and this is implicit right here in blue. They're the same equation of a circle, but they are described differently. So we are going to be talking in this lesson about how do we work with this implicit equation to find a derivative, right? So let's go to example 1. Here's the circle. This is our circle of radius 5. So this is 5 and 5. And this is the equation x squared plus y squared equals 25. So to find dy dx, we take the derivative of both sides of this equation. And we're going to treat y as an inside function, right? So that's really the only big difference here. Is that y is going to be treated like an inside function. So to take the derivative, I just am differentiating both sides with respect to x. So we're differentiating both sides of the equation with respect to x. The right side is just 0 because the derivative of 25 is 0. The left side, the derivative of x squared is just 2x. But then when I think about the derivative of y squared with respect to x, it's like we're going to think of the derivative of y squared with respect to y, which is 2y, and then multiply that by the derivative of y with respect to x, right? So if you want to think about it as inside and outside, the inside function is y, the outside function is x squared, in prime is dy dx, or y prime, and out prime is 2x, right? So out prime of in becomes 2y, and then in prime is dy dx. So my derivative of this whole thing is 2y dy dx. So I put that down here. And now I just have to isolate dy dx on the left side. So I'll say 2y dy dx equals minus 2x, subtracting this guy on both sides. And then my final goal is to just have dy dx alone. So I divide both sides by 2y. And I get my final answer, dy dx is equal to negative x over y, because the 2's are going to cancel out. So there it is. That's my slope at any point, slope of the tangent line at any point on the circle. We can do a couple common sense checks and see, well, if I'm up here, for example, at 0, 5, that's the top of the circle. If I'm at 0, 5, and I want to find the slope of my tangent line right there, it looks like it should come out to be 0, right? Let's check. Dy dx using this equation here. And this is a new notation. We put a long line, right? And you evaluate it at any point. So that dy dx at 0, 5, put in 0 for x and 5 for y. And that is equal to 0. So that makes sense because the slope here at that point of the tangent line is 0. If you were to look at another point, like maybe right here, and that's the point, that's not a very good tangent line. Let me redraw that. Let me do it in green and be right at the edge. So it's that point there. So finding the slope of the tangent line at 5, 0, right? So we do dy dx at 5, 0, and we would get negative 5 divided by 0, right? Which of course you cannot do. So we're really going to be getting like negative infinity, which makes sense because here we have a vertical tangent line. It's negative because if you think about all of the slopes here in the first quadrant of all these tangent lines is negative, more and more negative, more and more negative, and then right at the edge there it becomes sort of infinitely negative. So it all makes sense, and we were able to find that equation by implicit differentiation. Next thing is, okay, now that we have dy dx, can we write the equation of a tangent line at the point 3, 4, right? So let me just come here and erase some of this. So 3, 4 would be right here on this circle. 3, 4 is right there, right? So I'm trying to write the equation of that tangent line. And the way I would do it is, anytime you need the equation of a tangent line, you need a point that's given to you, 3, 4, and you need a slope. In this case, we have our dy dx, and we want to evaluate that at 3, 4. So we just come in and use the equation negative x over y, this guy up here, and we're going to get negative 3 over 4 is the slope. So this is my m, and I can write y minus y1 is equal to m times x minus x1. Super easy, not a big deal. Okay. Okay, so let's do another example now. This is a more interesting implicit equation, x cubed plus y cubed equals 6xy. It's called the folium of Descartes. It's this funky curve right here. And so let's find dy dx. I'm going to use y prime notation here. I could use dy dx if I wanted. So taking the equation, and first job will be to differentiate both sides with respect to x. So 3x squared plus, now here I'm thinking y is an inside function, the cubing is the outside function. So my out prime of in, or my f prime of g, is 3y squared, and then my g prime or my in prime is dy dx, which I'm going to write as y prime actually. So y squared y prime is equal to, now here I have a product, right? So I'll do 6x times the derivative of y plus y times the derivative of 6x, which is 6, using the product rule. Now, anything that has y prime or dy dx needs to come to the left side. Anything that doesn't have y prime needs to stay on the right side. So these terms, right, the 6y and the 3x squared, those need to be on the right side. And the other terms, collect them on the left side. So I'll get 3y squared y prime minus 6xy prime is equal to 6y minus 3x squared. And now you notice that we put everything with a y prime on the left side, which means y prime is a common factor that I can pull out and write the left side like this. And so now I can solve for y prime, isolate y prime by itself. So y prime, remember, is the same thing as dy dx. So this equation is equal to dy dx, or y prime. Okay, so now we have that equation, and we're asked to write the tangent line at 3, 3. So here's my point. Half the problem is done. My slope, which is dy dx at 3, 3, well, I have this equation that I just found right here, this guy. So I'm just going to put 3 in for x and y in there. I get 6 times 3 minus 3 times 9 over 3 times 9 minus 6 times 3. So I think it's 18 minus 27 over 27 minus 18, which is negative 9 over 9, or 1. Negative 1 is my slope. So if my slope is negative 1 and my point is 3, 3, then y minus 3 is equal to negative 1 times x minus 3 is my tangent line equation at 3, 3. So that's basically saying we have come to the point 3, 3. That's, let's see, 3 and 3. So that's right here. And we've written the equation of that line right there. That's what we just did. Okay, not a big deal. Next one, at what point is the tangent line horizontal, right? So we've got this dy dx, which is equal to 6y minus 3x squared over 3y squared minus 6x. So we want a horizontal tangent line means dy dx has to be equal to 0. So you take that whole big equation, set it equal to 0, right? So now you can think of this a few ways. It's like a rational function. You can cross multiply. So basically, the numerator has to be 0 for us to have a horizontal tangent line. So now you solve this and you say, well, that means 6y equals 3x squared, or y equals x squared divided by 2, okay? This is not it didn't give us an xy point. It just gave us a relationship between x and y. So we will take that relationship and go back into the equation for the curve, right? By that I mean the original equations, x cubed plus y cubed equals 6xy. So I'll go back to that original equation, and I'm going to put this guy into that. So then I would get x cubed plus x squared over 2y cubed, right? Because I've taken this y, oops, that's not what I wanted to do. I've taken this y and put it in here. That's this x squared over 2. So take that and then do that again here. So I get here is equal to 6x times x squared over 2. Okay, and then from here we're trying to solve this equation. So x cubed plus x to the 6th over 8 is equal to 3x cubed. And then I can multiply everything by 8, so I get 8x cubed plus x to the 6th equals 24x cubed. And then put everything on the left side, so x to the 6th minus 16x cubed is equal to 0. Factor out an x cubed, and we have now solved the equation. My two solutions will be x cubed equals 0, which means x is 0. That's 1. And x cubed minus 16 equals 0, which means x equals the cube root of 16, which is, as a decimal, it's 2.519. So those are the two places on this curve. It said find the two places, or the places where we have a horizontal tangent line. I guess we should also find the y's, right? So the y we know, remember, y is equal to x squared over 2 is what we were using. So y here would be 0, and y here would be 16 to the 1/3, that's the cube root of 16 squared, that's the x squared over 2. So I guess it would be 16 to the 2/3 divided by 2, and you could find a number for that in your calculator. Bottom line is that those two places are here, right here, 0, x equals 0, right, and x equals roughly 2.5. So it is roughly here. Those look about right in terms of places where I have horizontal tangent lines. Okay, let's talk about vertical tangent line, right? So vertical tangent line means the dy dx equation has to be infinite, basically, right? So you write your dy dx equation, that was 6y minus 3x squared over 3y squared minus 6. So if you want a vertical tangent line, right, the denominator has to be 0. This denominator has to be 0. So we set that equal to 0, and we do the same thing. We try to first find a relationship between x and y. So I'll solve this guy, and I'll get x is equal to y squared over 2. And I'll take this and put it back into the original equation. So I had the original equation, x cubed plus y cubed equals 6xy. I'll plop this in there, and I get y squared over 2 to the power 3 plus y cubed equals 6 times y squared over 2 times y, right? So what I'm doing is taking this guy and putting it in for x everywhere. And so then it ends up being y to the 6th, actually kind of similar to what happened last time, except it's the y's this time. So this will solve again to, it'll actually solve to those same exact two numbers that we got for x, because it works out like this. So y is equal to 0, or y is equal to the cube root of 16, which is 2.519. The corresponding x's, I use x is equal to y squared over 2. So x is equal to 0, And here I would get x is equal to 16 to the 1/3 squared over 2. So that would be 16 to the 2/3 over 2. And you can get a decimal out of that, right? So vertical tangent lines are at those two spots, 0, 0, as well as 16 to the 2/3 over 2. I want to check what that number is. So 16 to the 2/3 over 2 works out to be 3.1748, right? So my other point of vertical tangent line would be 3.1748, comma, 2.519. So I want to now just go back and look at my curve and see if that kind of makes sense. So I'm saying there's a vertical tangent line here because notice that if you look at the other branch of the curve, there is a vertical tangent line also at 0, 0. And the other one we're claiming is at, where did that go? 3.17, comma 2.5. Okay, so 3.17, comma 2.5 is about here. Yeah, so that makes sense as well. There is a vertical tangent line there. Okay, so moving on to the next example, let's do some trig. So we've got this guy here. Same idea, except trig functions to find this is an implicit equation, right? Sine of x plus y, and then on the other side, y squared cosine x. We're just going to leave the equation just like that and differentiate both sides implicitly. So this side will be cosine of x plus y, right? So now I have an inside function, which is x plus y, and an outside function, which is sine. So out prime of in times in prime. The in prime will be 1 plus dy dx. And this has to be equal to, here I have a product, right? So we've got two things multiplied. So first times the derivative of the second, it's negative sign, so I can put the negative out here, plus the second, which is cosine x, and then y squared, remember y is an inside function, so 2y dy dx. Okay, so that's the first step. Be careful now to distribute this properly. It's cosine x plus y times 1 and cosine x plus y times dy dx. So my goal is to put all the dy dx terms on the left. So, or y prime, question said y prime, so maybe I'll just call these guys y prime. And so we want all the y prime terms on the left. So first step might be to go cosine of x plus y times y prime, that's one term, and the other term is just first term here, just cosine of x plus y. And then on this side we have negative y squared sine x plus, I would actually write it as 2y y prime cosine x, just to make sure that all this doesn't look like it's inside the cosine function. Okay, so then on the left, I'll put y prime cosine x plus y minus 2y y prime cosine x, and on the right, I'll put everything else, minus y squared sine x plus cosine x plus y. Now factor out this y prime right here, and I get y prime times cosine of x plus y minus 2y cosine x is equal to minus y squared sine x plus cosine of x plus y. And then divide everything by whatever you have to divide by. That would be all of that to get y prime alone on the left. So y prime equals negative y squared sine x minus cosine of x plus y all over cosine of x plus y minus 2y cosine x. So a bit of a pain, but doable in terms of finding an equation for dy dx. Okay, here's my last problem. I have x to the fourth plus y to the fourth equals 16. This actually, if you plot it out, it's kind of interesting. It's like a kind of a squarish circle. It's like a flattened out circle or something like that, and it'll have radius 4. So anyway, we want to find now y double prime, right? So this is the new thing, and to do that, we're going to first find y prime and then y double prime. So y prime is dy dx, and just so you know, y double prime is d squared y dx squared. So if you see that written as d squared y dx squared or y double prime means the same thing. Okay, starting with y prime. Differentiate both sides. 4x cubed plus 4y cubed dy dx is equal to 0. So dy dx, pretty easy. It's just negative 4x cubed over 4y cubed, or in other words, negative x cubed over y cubed. Okay? Now, here it gets a little more tricky because I now have to differentiate this guy, this dy dx, which is negative x cubed over y cubed. That's another implicit equation. I'm going to differentiate it a second time now to get d squared y dx squared or y double prime, right? So now when I differentiate this side here, I have to do the quotient rule. So I'm going to get low d high minus high d low. Now d low, again, remember y is an inside function, so 3y squared dy dx. So low d high minus high d low over low low or low squared. And you can clean this up just a little bit by putting in dy dx. Actually, you have to put in dy dx because you don't want to leave any dy dx terms in your d squared y dx squared. This has to be all in terms of x and y. You can only have x's and y's. So we've got to put this guy in for dy dx. So we're going to get negative 3x squared y cubed plus 3x cubed y squared times negative x cubed over y cubed, all over y to the sixth, right? And you can clean this up at least a little bit by just saying, well, this plus and minus becomes a minus, and then, these y squareds will cancel, and, I'd have just one y on the bottom. So you can clean it up a little. You might even clean it up some more. But that's basically d squared y dx squared. Okay, a couple last comments about this last example. If you wanted horizontal and vertical tangent spots, right, you take the dy dx equation. For horizontal, you set dy dx equal to 0 and solve. So let's actually just do that. In this case, dy dx was negative x cubed over y cubed. That would be equal to 0. That means negative x cubed equals 0 or x equals 0. That's your x value where you have a horizontal tangent. To get the y value, you got to go back to the original equation, x to the fourth plus y to the fourth equals 16, and put this 0 in. So y to the fourth equals 16, y equals plus or minus 2. Those would be the places where we have a horizontal tangent line, 0 and plus or minus 2. By the way, I think earlier when I told you this was a squat circle, I made a slight error. The radii sort of would be not really radii, but the x and y intercepts would be at 2 and negative 2. So yeah, that makes sense then in terms of the horizontal tangent line. Vertical tangent line, you would say y cubed, the denominator of the dy dx, has to be equal to 0. So y equals 0, which means then x is going to come out to be plus or minus 2. So those are plus or minus 2 comma 0. Those would be the points where you have a vertical tangent line, which makes perfect sense. Those would be over here. Okay, so our takeaways are that equations can be explicit or implicit. That's number one. Explicit or implicit. We can differentiate implicit functions. We can differentiate implicit functions. We do not have to make them explicit. And to do differentiation implicitly, we are basically doing d dx of both sides. Treat y as an inside function using the chain rule. And then we're going to isolate y on dy dx on the left side. That's basically the recipe. these kind of have a recipe pattern to them, these problems, and yeah, that should get you through most of the homework, and I hope to see you guys soon. Bye.